Welcome to the VFD lesson. This lesson we will talk about the rectifier circuit. First we'll talk about the main components of the rectifier circuit, that is the diode. Diode we have A, K, and this is a picture of a typical diode. And the characteristic of the diode, the performance is like this. Here is the voltage across A and K. Here is the current. You can see this curve is the forward performance. And the forward, the current can go through the diode and with a very low voltage drop. And this curve is a reverse performance, have a very, very low leakage current. So basically, the diode is one directional components. The current can only flow through one direction, cannot go with the other direction. And this is a typical three-phase rectifier bridge, convert AC to DC. You can see here is a three-phase AC waveform. Here is a rectified DC voltage. And from engineering point of view, the output voltage, DC voltage, is 1.3 times the input line voltage. This is RMS voltage. This is the DC voltage average. For example, for the AC 380 system, the DC voltage will be roughly 513. For 690, it's about 930. This is standard 6-pulse rectifier from the power supply and the 3-phase rectifier and the output. 6 pulse means in one cycle, in one, like for example, for the 50 Hertz, is about 20 millisecond. During one cycle, 20 millisecond or 300 degree electric degree, and there will be 6 times current change, 6 times change of current path. So that is why we call it 6-pulse rectifier. And on the output DC voltage in one cycle, 360 degree or 20 millisecond, you can see 6 times of ripple on the rectified voltage. And the 12-pulse, you have 2 sets of standard 6-pulse rectifier and feed from different transformer. Secondary. Those 2 secondary, they have 3 30-degree phase shift, Y and delta. Then they form as a 12-pulse rectifier. So for the 12-pulse rectifier, on the DC side, in one cycle, for example, 20 millisecond, there will be 12 ripples instead of 6 ripples. So the more the number of ripples, the lower the ripple voltage. That means the voltage is more close to the DC. And if we look at the input current of the rectifier for the 6-pulse rectifier, for example, red one is A phase current, blue one is B phase, green one is C phase. So for one phase, the voltage is current is like this. And if we set with the 12-pulse and 2 secondary with 30-degree phase shift, then because of the phase shift, the input current will be much better, will be like this. It's more close to sinusoidal because most of harmonics will be cancelled because of the phase shift. We can see the harmonic bar of 6-pulse and 12-pulse. For example, for the 6-pulse rectifier, the harmonic will be the 5, 7, 11, 13, 17, 19, and so on. This is the order of the harmonics. So there will be a formula. K This is the harmonic order of the rectifier, the input current. P is the number of pulse, 6 pulse or 12 pulse. K is a natural number from 1, 2, 3, 4, plus minus 1. So for the 6 pulse, you have a 5, 6, 11, 13, 17, 19, and so on. For the 12 pulse, you have 11, 13, 23, 25. You don't have the 5 and 7 and 17 and 19. So it will be cancelled theoretically. But actually, from engineering point of view, there's still some harmonics left, but with very low level. So 6 pulse, all those harmonics will be there. 5, 7, 11, 13. But for the 12 pulse, you only have 11, 13, 23, 29, 25, 35, 37. And those harmonic will be cancelled. So the total harmonic will be much lower for the 12 pulse compared with the 6 pulse. So if we compare with the typical current distortion with the first one, like 6 pulse with a 2.5% line reactor, and this one with the 12 pulse with line reactor. The third one is 30 pulse. So the more the number of pulse, the lower the current harmonic distortion. So multiple pulse is a very effective way to reduce the current harmonic of input current. So this is all for today's lesson. You can scan the code to get more information. Thank you.